darkness, silence, and between every atom of your body, between every star in the night sky, an invisible force weaves through the fabric of reality itself. Gravity, the cosmic sculptor that shapes everything from the fall of a single raindrop to the spiraling dance of galaxies across billions of light years. It holds you gently against the Earth right now, a constant companion you've felt every moment of your life, yet never truly seen. For centuries, humanity believed this force acted instantaneously across any distance, connecting all matter in the universe through some mysterious action at a distance. But what if gravity, like light, has a speed limit? What if the sun's gravitational embrace doesn't reach us the moment it's generated, but travels across space like ripples spreading across a cosmic pond? Tonight, as you rest in comfort and safety, we'll embark on a journey through one of physics' most beautiful mysteries. We'll travel from ancient Greece to the cutting edge of modern science, from Newton's orchards to Einstein's thought experiments, from theoretical predictions to billion-dollar detectors capable of measuring distortions smaller than an atomic nucleus. We'll explore how scientists finally answered a question that had puzzled humanity for generations. Exactly how fast does gravity travel? The answer, when it came, would shake our understanding of reality itself. It would reveal that space-time is not a rigid stage where cosmic events unfold, but a dynamic, flexible fabric that can ripple and wave. It would show us that we're not merely observing the universe, but listening to it, hearing the cosmic symphony of colliding black holes and merging neutron stars through gravitational waves that wash over us at the speed of light. As you settle deeper into relaxation, imagine that if the sun suddenly vanished from the center of our solar system, Earth wouldn't immediately fly off into the darkness. We'd continue orbiting the empty space, where our star once was for precisely 8 minutes and 20 seconds, the exact time it takes light to cross the 93 million miles between the sun and Earth. Only then, simultaneously with the arrival of the last photons of sunlight, would we feel the gravitational change and begin drifting into the cosmic void. This isn't science fiction or speculation. It's confirmed fact, proven by some of the most extraordinary scientific instruments ever built and some of the most elegant observations ever made. The story of how we discovered gravity's speed is a testament to human ingenuity, persistence, and our deep need to understand the fundamental nature of reality, so relax completely. Let the gentle pull of Earth's gravity cradle you as we explore the invisible currents of space-time that connect everything in existence. Feel the weight of your body against the surface beneath you, a constant reminder that gravitational influence is real, tangible, and yet remains one of the deepest mysteries in all of physics. The journey ahead will take us through centuries of scientific revolution, through the minds of history's greatest thinkers, and into the hearts of cosmic cataclysms occurring billions of light years away. We'll ponder questions that blur the boundary between physics and philosophy, between the measurable and the metaphysical. And throughout it all, we'll return again and again to that central question: how fast does gravity travel, and what does the answer reveal about the universe we inhabit? But before we can understand the speed of gravity, we must first understand gravity itself. And to do that, we need to travel back in time, to an era when the night sky was humanity's greatest mystery and falling objects seemed to follow rules ordained by the gods themselves. The ancient world was filled with theories about why things fall. The Chinese proposed that all things contain proportions of yin and yang, with heavy objects naturally seeking their place in the earth. In India, philosophers suggested that objects fell due to an inherent property called gurutva, but it was the ancient Greeks who would develop the most influential early theory of gravity, one that would dominate Western thought for nearly 2,000 years. Aristotle, perhaps the most influential philosopher in human history, taught that the cosmos was ordered according to natural places. Earth and water, being heavy, naturally sought the center of the universe, which he believed was the center of the earth itself. Air and fire, being light, naturally rose toward the celestial spheres. This wasn't a force pulling objects down, but an inherent tendency. a desire of matter to reach its natural resting place. According to Aristotle, heavier objects fell faster than lighter ones because they had a stronger desire to reach their natural place. A stone fell faster than a feather because it contained more earthly essence. This theory felt intuitively correct, matching everyday observation. After all, if you drop a stone and a feather simultaneously, the stone does indeed hit the ground first. But Aristotle's theory had problems. It couldn't explain why objects accelerated as they fell. It couldn't account for the trajectories of projectiles. And most critically, it was simply wrong, though it would take nearly 2 millennia for someone to prove it. The ancient Greeks also pondered whether gravitational effects were instantaneous. In their geocentric model of the cosmos, with Earth at the center and celestial spheres carrying the sun, moon, planets and stars, the question didn't seem urgent. But some philosophers, particularly the atomists like Democritus, wondered whether influences could propagate through the void between atoms. If everything was made of atoms moving through emptiness, how did distant objects influence each other? This question would echo through the centuries, eventually leading to profound insights about the nature of forces and the speed at which they propagate. As you rest comfortably, imagine those ancient philosophers gazing at the night sky, watching the moon's steady progression through the constellations, observing Mars's retrograde motion, tracking the sun's annual journey. They had no telescopes, no mathematics of motion, no concept of inertia or momentum. Yet they asked the right questions that would eventually lead humanity to understand that gravity isn't a property of matter seeking its natural place, but a fundamental interaction shaping the structure of space-time itself. For nearly 2,000 years, Aristotle's physics dominated, but in the late Renaissance, everything began to change. The scientific revolution was about to dawn, and with it would come the first mathematical description of gravity and the first hints that gravitational effects might not be instantaneous. Galileo Galilei, born in Pisa in 1564, was a rebel from the start. He questioned authority, trusted observation over dine and coming, ancient texts, and had the mathematical genius to describe motion in precise quantitative terms. Legend tells us that he climbed the famous Leaning Tower of Pisa and dropped objects of different weights, demonstrating that they hit the ground at the same time, contrary to Aristotle's predictions. Whether this particular experiment occurred exactly as described is debatable. But Galileo definitely performed careful experiments showing that in the absence of air resistance, all objects fall at the same rate. This was revolutionary. It meant that gravity wasn't about heavy objects having a stronger desire to reach their natural place. Instead, all objects experience the same acceleration due to gravity, regardless of their mass. Galileo rolled balls down inclined planes, carefully measuring their acceleration and discovering that they followed precise mathematical laws. He found that the distance fallen was proportional to the square of the time elapsed, a relationship we now write as d equals half g(t) squared. Galileo's work on falling bodies and projectile motion laid the groundwork for a mathematical science of motion. But he didn't develop a theory of what gravity actually was or how it worked. That task would fall to a solitary genius working in England during one of history's darkest periods. In 1665, the Great Plague swept through London, killing thousands. Cambridge University closed, sending students and fellows home to avoid the pestilence. Among them was a young man named Isaac Newton, who returned to his family's farm in Woolsthorpe, Lincolnshire. There, in isolation, Newton's mind exploded with insights that would transform physics forever. The famous story tells of Newton sitting in a garden when an apple fell from a tree, inspiring him to wonder whether the same force pulling the apple downward also kept the moon in its orbit around Earth. This story, while probably embellished, captures something profound. Newton made a conceptual leap that seems obvious in hindsight, but was revolutionary at the time. Perhaps terrestrial gravity and celestial mechanics were governed by the same force. By 1687, Newton had developed his ideas into a complete theory of motion and gravitation, published in his masterwork, Philosophiae Naturalis Principia Mathematica, perhaps the most influential scientific book ever written. In the Principia, Newton presented his three laws of motion and his law of universal gravitation, which stated that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, Newton's law is elegantly simple. F equals gm 1m2 divided by r squared. This single equation explained everything from falling apples to planetary orbits, from the tides to the behavior of comets. It was a triumph of mathematical physics, showing that the cosmos operated according to precise, universal laws that human minds could comprehend. Newton's theory worked extraordinarily well. Using it, astronomers could predict planetary positions centuries in advance. They could explain the complex motions of the moon. They could account for the tides through the combined gravitational influences of the moon and Sunday. When Uranus's orbit showed slight irregularities that couldn't be explained by known planets, astronomers used Newton's equations to predict where an unknown planet must be, and Neptune was duly discovered almost exactly where the mathematics predicted. But Newton's theory contained a troubling feature that bothered Newton himself. His equations implied that gravitational effects propagated instantaneously across any distance. If the Sun moved, Earth would feel the change in gravitational pull immediately, with no delay whatsoever. This seemed to require what Newton called action at a distance, the idea that objects could influence each other across empty space without any medium or mechanism connecting them. In A Letter to Richard Bentley in 1692, Newton wrote, "That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe, no man who has in philosophic matters a competent faculty of thinking could ever fall into it." Despite his own discomfort with instantaneous action at a distance, Newton's mathematics didn't specify how fast gravity traveled, and the equations worked perfectly by assuming instantaneous propagation. For over 2 centuries, this assumption went largely unchallenged. The question of gravity's speed seemed academic, a philosophical concern with no practical implications. But as you drift deeper into relaxation, consider what instantaneous gravity would mean. If the Sun suddenly vanished, Earth would immediately fly off in a straight line, even though the last light from the Sun would take over 8 minutes to reach us. We'd somehow know about the Sun's disappearance before we could see it, before any light or information could reach us. This seems to violate a basic intuition about causality. How can we know about an event before information about it arrives? This tension between Newton's instantaneous gravity and our intuition about causality would remain unresolved for 200 years. But in the 19th century, a parallel revolution in physics would raise the question anew, suggesting that if electromagnetic effects travelled at a finite speed, perhaps gravity did too. The 19th century witnessed the unification of electricity and magnetism, one of physics' great triumphs. Through the work of scientists like Hans Christian Ørsted, André-Marie Ampère, Michael Faraday, and culminating with James Clerk Maxwell, it became clear that electricity and magnetism were 2 aspects of a single electromagnetic force. Maxwell's equations, published in complete form in 1865, showed that oscillating electric and magnetic fields could propagate through space as waves traveling at a specific velocity. When Maxwell calculated this velocity using the known constants of electromagnetism, he got approximately 310,740 kilometers per second. This was remarkably close to the measured speed of light, about 299,792 kilometers per second. Maxwell realized this couldn't be a coincidence. Light itself must be an electromagnetic wave, oscillations of electric and magnetic fields propagating through space at the speed determined by electromagnetic constants. This was a stunning unification, connecting optics to electromagnetism and revealing that light, electricity, and magnetism were intimately related phenomena. But Maxwell's work raised an intriguing question. If electromagnetic effects propagated at the speed of light rather than instantaneously, why should gravity be different? Shouldn't all fundamental forces have finite propagation speeds? Some physicists began to wonder whether Newton's instantaneous gravity was an approximation that worked well for most purposes but might break down in extreme circumstances. The French mathematician Henri Poincaré was among the first to seriously consider gravity propagating at light speed. In a 1905 paper, he suggested that a relativistic theory of gravity should have gravitational disturbances propagating at the speed of light, consistent with the emerging principle of relativity that no information could travel faster than light. Meanwhile, astronomers had noticed a puzzling anomaly in Mercury's orbit. Mercury, the innermost planet, follows an elliptical path around the Sunday. The point of its closest approach to the Sun, called the perihelion, gradually shifts over time, causing the orbit to precess. Most of this precession could be explained by the gravitational influences of other planets, particularly Venus, Earth, and Jupiter, which tug on Mercury and cause its orbit to rotate slowly. But there was a problem. Even accounting for all known gravitational influences, Mercury's perihelion precessed about 43 arcseconds per century faster than Newton's theory predicted. 43 arcseconds is tiny, less than 1/100th of a degree per century, but it was real and unexplained. Some astronomers proposed an undiscovered planet closer to the Sun than Mercury, which they named Vulcan, but no such planet was ever found. This tiny discrepancy in Mercury's orbit would turn out to be crucial evidence for a revolutionary new theory of gravity, one that would finally answer the question of how fast gravitational effects propagate. As you rest peacefully, imagine the state of physics at the dawn of the 20th century. Newton's mechanics had reigned supreme for over 200 years, explaining virtually everything from falling apples to planetary orbits. Maxwell had unified electricity, magnetism, and light into a single electromagnetic theory. The universe seemed mostly understood, with just a few small puzzles remaining. But those small puzzles, including Mercury's anomalous precession and the nature of light's propagation, would crack open the foundations of physics, leading to two great revolutions: relativity and quantum mechanics. And in resolving these puzzles, humanity would discover that gravity isn't a force at all, but something far stranger and more beautiful. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would change physics forever. Albert Einstein's miracle year included papers on the photoelectric effect, Brownian motion, and 2 papers on what would become known as special relativity. Special relativity arose from Einstein's deep thinking about the nature of light and motion. Maxwell's equations predicted a specific speed for light, but speed relative to what? Light in the 19th century was thought to propagate through a medium called the luminiferous ether, just as sound propagates through air. But experiments trying to detect Earth's motion through the ether kept failing. The Michelson-Morley experiment of 1887 found no evidence of an ether wind, suggesting that light traveled at the same speed regardless of the observer's motion. Einstein took a radical approach. What if the ether didn't exist? What if light always traveled at the same speed, approximately 299,792 kilometers per second, regardless of the motion of the source or observer? This seemingly simple postulate, combined with the principle that the laws of physics should be the same in all inertial reference frames, led to revolutionary conclusions. Time and space weren't absolute, as Newton had assumed. Instead, they were relative, dependent on the observer's state of motion. Moving clocks ticked slower. Moving objects contracted in length. Simultaneity wasn't absolute. Events that appeared simultaneous to one observer might occur at different times. according to another observer moving relative to the first. Most importantly for our story, Einstein's special relativity established the speed of light as a cosmic speed limit. Nothing could travel faster than light, not even information. This directly challenged Newton's instantaneous gravity. If gravitational effects propagated instantaneously, they could carry information faster than light, violating the fundamental principle of relativity. Einstein knew his theory of special relativity was incomplete. It described physics in inertial reference frames, those moving at constant velocity, but didn't account for acceleration or gravity. Over the next decade, Einstein struggled to develop a theory of gravity consistent with relativity. The task was extraordinarily difficult, requiring him to master the complex mathematics of curved spaces and to develop entirely new conceptual frameworks. The breakthrough came through what Einstein later called his happiest thought. In 1907, he realized that someone falling from a roof wouldn't feel their own weight during the fall. In the freely falling reference frame, the effects of gravity disappeared, at least locally. This suggested a deep connection between gravity and acceleration, what Einstein called the equivalence principle. The equivalence principle states that there's no local experiment you can perform to distinguish between being in a gravitational field and being in an accelerating reference frame. Standing on Earth's surface, you feel weight pulling you down, but you'd feel exactly the same sensation if you were in a rocket accelerating through empty space at 9.8 meters per second squared. Locally, gravity and acceleration are indistinguishable. This principle led Einstein to a radical reconceptualization of gravity. Perhaps gravity wasn't a force at all, but a manifestation of curved spacetime. Massive objects don't pull on each other across space. Instead, they curve the fabric of spacetime itself, and other objects move along the straightest possible paths through this curved geometry. Imagine spacetime as a flexible rubber sheet. Place a heavy ball on the sheet, and it creates a depression. Roll a smaller ball past the depression, and its path curves around the dip. From the perspective of creatures living on the sheet's surface, it looks like the heavy ball is pulling the smaller ball toward it. But really, the smaller ball is just following a straight path through curved space. In November 1915, after years of intense work, Einstein presented his general theory of relativity to the Prussian Academy of Sciences. The theory was built on elegant but complex mathematics, describing gravity through the Einstein field equations, which relate the curvature of spacetime to the distribution of matter and energy within it. General relativity made several testable predictions that differed from Newton's theory. It predicted that starlight passing near the Sun would be bent by the Sun's gravitational field with twice the deflection. Newton's theory predicted. It explained Mercury's anomalous perihelion precession perfectly, accounting for the 43 arc-seconds per century that had puzzled astronomers. And most importantly for our story, it predicted that changes in gravitational fields would propagate as waves traveling at exactly the speed of light. According to general relativity, when massive objects accelerate, they create ripples in spacetime itself, gravitational waves that spread outward at light speed. These waves alternately stretch and compress spacetime as they pass, carrying energy away from accelerating masses. The existence of gravitational waves and their propagation speed were direct consequences of Einstein's equations. This solved the problem of action at a distance. In general relativity, gravitational effects don't act instantaneously across space. Instead, changes in the gravitational field propagate at light speed, respecting the cosmic speed limit. If the Sun suddenly vanished, Earth would continue, orbiting the empty space for 8 minutes and 20 seconds, exactly the time it takes light to travel from the Sun to Earth. The prediction was clear and unambiguous. Gravity travels at the speed of light. But how could scientists test this prediction? Gravitational waves, if they existed, would be extraordinarily weak by the time they reached Earth. Detecting them would require measuring changes in distance smaller than an atomic nucleus over lengths of several kilometers. Such precision seemed impossible with 1,000 915 technology, or indeed with the technology of any foreseeable future. As you sink deeper into comfort, imagine Einstein's equations describing how space-time curves around massive objects, how these curves guide the motion of planets and stars, and how accelerating masses send ripples spreading through the fabric of reality at light speed. The universe he described was dynamic, flexible, alive with gravitational waves connecting all matter through space-time's invisible currents. But proving this beautiful theory would require more than mathematics. It would require catching those invisible waves, measuring their speed, and confirming that gravity really did travel at the speed of light. That quest would take a century and represent one of the greatest technological achievements in human history. The first test of general relativity came in 1919, just 4 years after Einstein published his theory and 1 year after World War I ended. Arthur Eddington, a British astronomer, led an expedition to observe a total solar eclipse from Principe, an island off the west coast of Africa, while another team observed from Sobral, Brazil. During the eclipse, when the sun's bright disk was covered by the moon, Eddington photographed stars near the sun's edge. According to general relativity, the sun's mass should curve space-time around it, and starlight passing near the sun should follow this curved path, making the stars appear slightly displaced from their usual positions. Newton's theory also predicted some deflection, but only half as much as Einstein's theory. The photographs showed that starlight was indeed deflected, and by approximately the amount Einstein predicted. When the results were announced in November 1919, they made headlines worldwide. The Times of London proclaimed "Revolution in Science and New Theory of the Universe." Einstein became an international celebrity overnight, perhaps the most famous scientist in the world. But confirming light deflection, while important, didn't directly measure the speed of gravity. That would require detecting gravitational waves themselves and measuring how fast they travel. Through the mid-20th century, gravitational waves remained theoretical predictions, unobserved and perhaps unobservable. Some physicists even doubted whether gravitational waves were real physical phenomena. The mathematics of general relativity predicted them, but mathematical predictions don't always correspond to physical reality. Perhaps gravitational waves were mathematical artifacts, coordinate effects that disappeared in the right reference frame, carrying no real energy and producing no measurable effects. This debate was resolved in 1957 at a conference at the University of North Carolina. Physicist Felix Pirani presented a rigorous analysis showing that gravitational waves were real physical phenomena that carried energy. Hermann Bondi, another physicist at the conference, proposed a simple thought experiment. Imagine two masses connected by a spring with friction. As a gravitational wave passes, it alternately stretches and compresses the space between the masses, causing them to oscillate. The friction converts this oscillatory motion into heat, proving that gravitational waves carry real energy that can do real work. This settled the theoretical question, but detecting gravitational waves remained extraordinarily challenging. The problem is that gravity is by far the weakest of the four fundamental forces. Gravitational effects from cosmic sources are incredibly weak by the time they reach Earth. Even the most violent cosmic events, black holes merging, neutron stars colliding, produce gravitational waves that, after traveling millions or billions of light years, cause distortions in spacetime of less than 1 part in 10 to the power of 21. To put this in perspective, imagine measuring the distance from Earth to the nearest star, Proxima Centauri, about 4.2 light-years or 40 trillion kilometers, to an accuracy smaller than the width of a human hair. That's the level of precision required to detect gravitational waves. It seemed hopeless. Nevertheless, some physicists attempted detection. Joseph Weber, working at the University of Maryland in the 1960 seconds, built large aluminum cylinders that he hoped would vibrate detectably when gravitational waves passed through them. These Weber bars were carefully isolated from vibrations and monitored with sensitive instruments. In 1969, Weber announced that he had detected gravitational waves. His results suggested that massive gravitational wave sources were passing Earth constantly, far more frequently than theory predicted. The physics community was initially excited, but skepticism grew as other researchers built similar detectors and failed to replicate Weber's results. By the mid-1970s, the consensus emerged that Weber's detections were false positives, probably caused by environmental noise or instrumental artifacts. His bars simply weren't sensitive enough to detect the weak gravitational waves reaching Earth. But Weber's pioneering work inspired others to think seriously about gravitational wave detection, leading to new approaches and technologies. As you rest comfortably, picture these early detectors, massive metal cylinders suspended in vacuum chambers, their surfaces monitored by sensors waiting for the telltale vibration of a passing gravitational wave. The detection attempts failed, but they represented humanity's first serious effort to hear the universe in a new way, to catch the space-time ripples that Einstein had predicted decades earlier. The breakthrough in gravitational wave detection wouldn't come from Weber bars, but from astrophysical observations using some of the most precise clocks in the universe, pulsars. In 1974, Russell Hulse and Joseph Taylor, working at the Arecibo Observatory in Puerto Rico, discovered something extraordinary. They were surveying the sky with the giant radio telescope, looking for pulsars rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. As these beams sweep past Earth, we detect regular pulses of radio emission, sometimes hundreds of times per second. One pulsar, Hulse discovered, designated PSR B 1913+16, showed a peculiar pattern. Its pulse timing varied in a regular way, speeding up and slowing down over an 8-hour cycle. This indicated that the pulsar was orbiting another object, with the orbital motion creating a Doppler shift in the pulse timing. Further observations revealed that the companion was also a neutron star, creating a binary system of two incredibly dense objects orbiting each other at breakneck speed. This binary pulsar system provided an unprecedented natural laboratory for testing general relativity. The neutron stars, each with about 1.4 times the Sun's mass compressed into a sphere only about 20 kilometers across, orbited each other at high speeds in a highly elliptical orbit. At their closest approach, they came within about 750,000 kilometers of each other, closer than twice the Earth-Moon distance. According to general relativity, such a system should emit gravitational waves, carrying energy away from the orbit. As energy is lost to gravitational waves, the orbit should gradually shrink, with the two neutron stars spiraling slowly toward each other. This orbital decay would cause the orbital period to decrease by a tiny but measurable amount. Hulse and Taylor, along with colleagues, carefully timed the pulsar's pulses over many years. The measurements required extraordinary precision. Each pulse arrival time had to be measured to within microseconds, accounting for Earth's rotation, its orbit around the Sun, and many other effects. The accumulated data built up a detailed picture of how the orbit was evolving. The results were spectacular. The orbital period was decreasing by about 76 microseconds per year, exactly matching the predictions of general relativity for energy loss through gravitational wave emission. Over the decades since the discovery, this agreement has only improved as more data accumulated. The binary pulsar's orbit is decaying precisely as it should if gravitational waves carry energy away at the rate predicted by Einstein's equations. This didn't directly detect gravitational waves. The waves produced by the binary pulsar are far too weak to detect with any conceivable instrument, but it provided strong indirect evidence that gravitational waves exist and carry exactly the amount of energy that general relativity predicts. In 1993, Hulse and Taylor received the Nobel Prize in Physics for this discovery. The binary pulsar observations also provided indirect evidence that gravitational waves travel at light speed. The energy loss matched predictions based on waves propagating at light speed, not faster or slower. But physicists wanted direct detection, actually measuring gravitational waves as they passed Earth and confirming their propagation speed directly. By the 1980 seconds, a new approach to gravitational wave detection had emerged: laser interferometry. This technique promised sensitivity far beyond what Weber bars could achieve. The concept is elegant. Split a laser beam and send the two beams down perpendicular arms several kilometers long. Reflect the beams back with mirrors and recombine them. If both arms remain exactly the same length, the recombined light creates a stable interference pattern. But if a gravitational wave passes through, it stretches one arm while compressing the other, changing the interference pattern in a measurable way. This technique could potentially detect the tiny space-time distortions caused by gravitational waves, but building such a detector required solving enormous technical challenges. The laser had to be extraordinarily stable. The mirrors had to be suspended perfectly, isolated from all environmental vibrations. The vacuum tubes containing the laser beams had to be several kilometers long. The whole system had to be controlled with extraordinary precision. In 1992, after years of planning and design, the United States National Science Foundation approved funding for the Laser Interferometer Gravitational Wave Observatory, or LIGO. Two identical detectors would be built, one in Hanford, Washington, and another in Livingston, Louisiana, separated by about 3,000 kilometers. Having two detectors would help distinguish real gravitational wave signals from local noise. A true gravitational wave should appear at both detectors, while local disturbances would only affect one. Each LIGO detector consists of two 4-kilometer-long arms arranged in an L shape. Inside these arms, laser beams bounce back and forth hundreds of times between mirrors suspended by sophisticated isolation systems. These mirrors are among the quietest objects ever made, suspended by multiple stages of vibration isolation that filter out seismic noise. Even the tiny vibrations caused by ocean waves breaking on shores thousands of kilometers away. The sensitivity required is almost incomprehensible. To detect gravitational waves, LIGO needs to measure changes in the 4-kilometer arm lengths of less than 1/10,000th the width of a proton. At this scale, quantum effects become important. The laser light itself creates quantum noise, setting a fundamental limit on measurement precision. Engineers had to battle quantum mechanics itself to make LIGO work. Initial LIGO began operations in 2002, taking data through 2010. Despite the extraordinary sensitivity, no gravitational waves were detected during this period. The sources producing detectable gravitational waves merging black holes and neutron stars were simply too rare or too distant for initial LIGO's sensitivity. The detectors could only detect the strongest events within about 50 million light-years, a tiny fraction of the observable universe. But physicists had anticipated this. The plan all along was to upgrade the detectors, increasing their sensitivity by a factor of 10. This would increase the volume of space they could survey by a factor of 1,000, making detections far more likely. Between 2010 and 2015, LIGO underwent a major upgrade to advanced LIGO configuration, incorporating new mirrors, more powerful lasers, improved vibration isolation, and numerous other enhancements. As you drift deeper into relaxation, imagine the years of patient work that went into LIGO. Thousands of scientists and engineers, decades of development, hundreds of millions of dollars, all invested in detecting something that had never been observed directly and might not exist at all. It was one of physics' great gambles, a bet that Einstein was right, that gravitational waves were real, and that human ingenuity could build instruments sensitive enough to detect them. Advanced LIGO began operations in September 2015. Within days, it would detect something that would change physics forever. On the 14th of September 2015, at 9 hours 50 minutes and 45 seconds UTC, a gravitational wave passed through Earth. It stretched and compressed spacetime by about 1 part in 10 to the power of 21, a distortion far too small for any human to feel. but LIGO's exquisitely sensitive instruments detected it. The signal appeared first at the Livingston detector, then 7 milliseconds later at Hanford. The waveform was distinctive, a chirp that started at about 35 Hz and increased in frequency and amplitude over 0.2 seconds, reaching about 250 Hz before disappearing. The matched filtering algorithms that constantly analyzed LIGO's data immediately flagged the signal as a potential detection. Scientists working on LIGO couldn't believe it at first. The detectors had just started operating after the advanced LIGO upgrade. Was this really a gravitational wave, or some elaborate test signal? The collaboration has a policy of occasionally injecting fake signals to test the analysis pipeline, keeping most collaboration members unaware that it's a test until afterward. Could this be such an injection? But no injection had been scheduled. The signal was real. As word spread through the collaboration, excitement built. If this was a true detection, it would be one of the most important scientific discoveries in decades. Over the following months, the LIGO scientific collaboration subjected the signal to exhaustive analysis. Could it be a glitch in the instruments? Detailed investigation of the detector data showed no evidence of instrumental problems at the time of the signal. Could it be environmental noise? Seismic data, weather data, magnetic field measurements, everything was examined. Nothing could explain the signal except an actual gravitational wave. The waveform itself told a story. By comparing the observed signal to theoretical predictions for various sources, physicists determined that the gravitational wave came from two black holes merging. The system started with two black holes weighing approximately 36 and 29 solar masses orbiting each other. As they spiraled inward, they emitted gravitational waves, losing energy and orbiting faster and faster. The frequency of gravitational waves from such a system is twice the orbital frequency. As the black holes orbited faster, the gravitational wave frequency increased, creating the characteristic chirp. In the final fraction of a second before merger, the black holes were orbiting at nearly half the speed of light, accelerating at forces that would seem unimaginable on human scales. When the black holes finally merged, they formed a single black hole with about 62 solar masses. But wait, 36 plus 29 equals 65 solar masses. Where did the missing 3 solar masses go? They were converted directly into gravitational wave energy through Einstein's famous equation, E equals mc squared. 3 times the sun's mass energy, released in a fraction of a second as gravitational waves, briefly making this merger the most powerful event in the observable universe, though only in gravitational waves, not in light. The energy released was staggering. For that brief moment, the gravitational wave luminosity exceeded the combined light output of all the stars in the observable universe. Yet this cosmic cataclysm occurred 1.3 billion light-years away, and the signal that reached Earth was almost impossibly faint, detected only by humanity's most sensitive instruments. The detection, designated GW150914, was announced to the world on the 11th of February 2016 at a press conference in Washington, D.C. The announcement made headlines worldwide. Scientists had directly detected gravitational waves for the first time, confirming a century-old prediction of Einstein's theory. It opened a new window on the universe, allowing humanity to observe cosmic events that emit little or no light, like merging black holes. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. The achievement represented one of humanity's greatest scientific accomplishments, the culmination of decades of work by thousands of people. But detecting gravitational waves was only part of the story. To measure the speed of gravity directly, scientists needed something more. They needed to detect both gravitational waves and electromagnetic waves from the same source and compare their arrival times. Black holes merging emit only gravitational waves. They produce no light because black holes, by definition, allow nothing to escape, not even light. To measure gravity's speed, scientists needed a source that emitted both gravitational waves and light. That opportunity came 2 years after the first detection. As you rest peacefully, imagine the gravitational waves from countless cosmic mergers washing over you right now. Most are too weak to detect, too distant, their signals lost in noise. But occasionally, somewhere in the vast universe, two massive objects spiral together and merge, sending out a brief burst of gravitational waves that travel across cosmic distances for millions or billions of years before reaching Earth. And now, for the first time in history, humanity can detect them, can listen to the cosmic symphony, can hear space-time itself singing. The stage was set for the measurement that would finally, definitively answer the question: how fast does gravity travel? On the 17th of August, 2017, at 12 hours 41 minutes and 4 seconds UTC, both LIGO detectors detected another gravitational wave chirp. This time, the signal was different from previous detections. It lasted much longer, about 100 seconds, rather than a fraction of a second, and oscillated at higher frequencies. Analysis quickly revealed the source: two neutron stars merging. Neutron stars are the ultra-dense remnants of massive stars that exploded as supernovae. A typical neutron star contains about 1.4 times the Sun's mass compressed into a sphere only about 20 kilometers in diameter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects represent matter in its most extreme state, short of black holes with density comparable to atomic nuclei. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves just like the binary pulsar Hulse and Taylor discovered. Eventually, after millions or billions of years, they merge, creating a cataclysmic collision that releases enormous energy across the spectrum, from radio waves to gamma rays. The gravitational wave signal from this merger, designated GW170817, was detected by both LIGO observatories. The European Virgo detector was also operating but saw a much weaker signal, which actually helped localize the source. The weak Virgo signal indicated the source was in Virgo's less sensitive direction, constraining the source location to a relatively small patch of sky. Within seconds of the gravitational wave detection, the LIGO-Virgo collaboration sent alerts to astronomical observatories worldwide, providing the best estimate of where in the sky the merger occurred. Telescopes began slewing toward the target region, searching for an optical counterpart. But before any optical telescopes could respond, another alert came in. Just 1.7 seconds after the gravitational wave signal arrived at Earth, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. Gamma ray bursts are among the most energetic explosions in the universe, and short gamma ray bursts, lasting less than 2 seconds, had long been suspected to come from neutron star mergers. Now, for the first time, that suspicion was confirmed. The near-simultaneous arrival of gravitational waves and gamma rays from the same event was extraordinary. But it was only the beginning. Over the following hours, days, and weeks, observatories around the world and in space observed the aftermath of the neutron star merger across the entire electromagnetic spectrum. About 11 hours after the merger, optical telescopes discovered a new point of light in the galaxy NGC 4993, located about 130 million light-years away in the constellation Hydra. This kilonova was the visible light emission from the merger, powered by the radioactive decay of heavy elements created in the collision. As the days passed, the kilonova faded and shifted toward redder wavelengths, exactly as theoretical models predicted. X-ray and radio telescopes detected emission from the merger site, revealing jets of material moving at relativistic speeds. The wealth of observational data from this single event exceeded what many scientists had hoped to see from neutron star mergers in their entire careers. It was a triumph of multi-messenger astronomy, combining gravitational wave observations with electromagnetic observations to learn far more than either could reveal alone. But buried in this wealth of data was the answer to our central question: how fast does gravity travel? The gravitational waves and gamma rays had traveled approximately 130 million light-years from NGC, 4,993 to Earth, a journey that took about 130 million years. The gravitational waves arrived 1.7 seconds before the gamma rays. This tiny difference over such an enormous journey provided the first direct measurement of the speed of gravity. Scientists analyzed the timing carefully. The 1.7-second difference didn't mean gravity traveled faster than light. Rather, it reflected the different mechanisms that produced the gravitational waves and gamma rays. The gravitational waves were emitted during the final seconds of the spiral, as the neutron stars orbited each other faster and faster. The gamma rays were produced after the collision, when jets of material punched through the surrounding debris and broke free into space. The emission delay explained the 1.7-second difference. The gravitational waves left first because they were produced by the spiraling orbit itself. The gamma rays followed because they were generated after the collision, once the merger dynamics produced the conditions for a gamma ray burst. The crucial point was that once both signals were produced, they traveled through space at the same speed. By analyzing the timing and accounting for the expected emission delay, scientists could constrain how fast gravitational waves traveled relative to light. The result was stunning. The speed of gravity differs from the speed of light by less than 1 part in 10 to the power of 15. For all practical purposes, gravity travels at exactly the speed of light. This was the measurement scientists had waited a century to make. Einstein predicted in 1915 that gravity propagates at light speed, and now, 102 years later, that prediction was confirmed to extraordinary precision. The cosmic speed limit applies not just to light and matter, but to gravity itself. The fabric of spacetime can ripple and wave, but those ripples travel at exactly the speed of light, no faster and no slower. The implications were profound. The observation immediately ruled out many alternative theories of gravity that predicted different propagation speeds. It confirmed that general relativity's description of gravity as space-time curvature was correct, at least in the regime tested by neutron star mergers. And it resolved the centuries-old question that had puzzled Newton. Gravitational effects don't propagate instantaneously, but at light speed, respecting the cosmic speed limit established by special relativity. As you sink deeper into restful sleep, consider what this means. Right now, at this very moment, the Sun is exerting gravitational influence on Earth. But this influence was generated about 8 minutes ago, when the gravitational field configuration left the Sunday. If the Sun suddenly vanished, we wouldn't know for 8 minutes exactly the same time it takes light to reach us. We'd continue orbiting the empty space where the Sun was, oblivious to its absence, until the information about its disappearance reached us at light speed. The universe operates on a cosmic time delay, with influences propagating at light speed rather than instantaneously. This ensures causality, prevents paradoxes, and maintains the orderly relationship between cause and effect that makes the universe comprehensible. The speed of gravity, precisely matched to the speed of light, is fundamental to the structure of reality itself. GW 170817 didn't just measure gravity's speed, it opened a new era of multi-messenger astronomy, where gravitational waves and light work together to reveal cosmic secrets neither could uncover alone. Since that first detection, dozens more gravitational wave events have been observed, mostly from merging black holes, but including several more neutron star mergers. Each detection refines our understanding of how these systems form and evolve, what happens during the final moments before merger, and how the fundamental forces of nature behave in their most extreme manifestations. Gravitational wave astronomy has become a mature field, and future detectors promise even greater sensitivity, able to detect mergers throughout most of the observable universe. But the question remains, could gravity ever travel faster than light under some circumstances? What do theoretical physics and the frontiers of quantum gravity have to say about the speed of gravitational influence? The experimental evidence is clear. Gravity travels at the speed of light. But science progresses by questioning established ideas and exploring edge cases where theories might break down. Let's explore whether there are any circumstances, however exotic, where gravity might exceed the cosmic speed limit. Einstein's special relativity established the speed of light as a universal cosmic speed limit based on simple postulates. The laws of physics are the same in all inertial reference frames, and light speed is constant for all observers. From these, Einstein derived the famous result that nothing with mass can reach or exceed light speed, and no information can travel faster than light. General relativity extended this speed limit to gravity. Changes in gravitational fields propagate as waves traveling at light speed. This isn't a separate postulate, but a consequence of how general relativity incorporates special relativity's principles. If gravity could travel faster than light, it would violate the causal structure that special relativity established. But could there be loopholes? Could quantum effects modify gravity's speed? Could extra dimensions provide shortcuts? Let's explore these possibilities. One early objection to finite speed gravity came from Pierre-Simon Laplace in the late 18th century. Laplace calculated that if gravity propagated at finite speed, planetary orbits would be unstable due to an aberration effect. Imagine Earth orbiting the Sunday. The Sun's gravitational pull would point not toward where the Sun is now, but toward where it was when the gravitational influence left the Sun about 8 minutes ago. This delay would create a tiny tangential component to the gravitational force, like shooting at a moving target and having to lead it. Laplace calculated that this aberration would cause planetary orbits to spiral outward rapidly, contradicting the observed stability of the solar system over billions of years. He concluded that gravity must propagate at least millions of times faster than light, effectively instantaneously. But Laplace's calculation missed crucial relativistic effects. In general relativity, the gravitational field doesn't just point toward where an object was, but includes velocity-dependent terms that exactly cancel the aberration for objects moving at constant velocity. The Earth orbits the Sun at nearly constant speed. The orbit is slightly elliptical, but the speed variations are small, so the aberration effect is almost perfectly cancelled. This cancellation is similar to how a charged particle, moving at constant velocity, produces electric and magnetic fields that combine such that the net force on another charged particle points toward where the first particle is. Now, not where it was when the electromagnetic influence left it. The finite propagation speed of electromagnetic fields doesn't destabilize orbits of charged particles, and similarly, the finite propagation speed of gravity doesn't destabilize planetary orbits. Only when masses accelerate significantly do gravitational waves carry away energy and cause orbits to decay. For the Earth-Sun system, this energy loss is completely negligible. It would take far longer than the current age of the universe for gravitational wave emission to significantly affect Earth's orbit. For the tight orbits of merging black holes or neutron stars, the effect becomes dramatic, but that's when we observe gravitational waves directly. So Laplace's objection doesn't hold. Planetary orbits remain stable even with gravity propagating at light speed, thanks to the velocity-dependent terms in Einstein's equations. But what about quantum mechanics? Could quantum effects allow gravitational influence to propagate faster than light? In quantum field theory, forces are carried by particles. The electromagnetic force is carried by photons, the strong nuclear force by gluons, the weak nuclear force by W and Z bosons. For gravity, the hypothetical carrier particle is the graviton, a massless spin 2 particle that has never been directly detected. In quantum field theory, massless particles like photons and gravitons must travel at light speed. The requirement comes from combining quantum mechanics with special relativity. A massless particle's energy-momentum relation is E equals pc, where p is momentum and c is light speed. This relation forces massless particles to travel at light speed in any reference frame. Could gravitons have mass? If gravitons had even a tiny mass, they would travel slower than light speed, and gravity would propagate slower than light. But observations severely constrain any possible graviton mass. The observation of GW170817, where gravitational waves and light arrived within 1.7 seconds after a 130 million light-year journey, constrains the graviton mass to less than about 10 to the power of negative 54 kilograms, an extraordinarily tiny limit. Effectively, gravitons must be massless, and massless particles must travel at light speed. Quantum mechanics doesn't provide a loophole for faster-than-light gravity, but wait, doesn't quantum mechanics allow seemingly faster-than-light effects through quantum entanglement? When two particles are entangled, measuring one particle instantaneously affects the other, regardless of the distance separating them. Einstein famously objected to this spooky action at a distance, arguing it violated relativity's prohibition on faster-than-light influence. Years of experiments have confirmed that quantum entanglement is real. Measuring one entangled particle does instantaneously affect its partner, even if they're separated by large distances. But crucially, this doesn't allow faster-than-light communication. The correlations between entangled particles are only revealed when measurement results from both particles are compared, and that comparison requires classical information to travel at light speed or slower. Similarly, if gravitational fields have quantum properties, which they almost certainly must, though we don't yet have a complete theory of quantum gravity, quantum entanglement might create correlations in gravitational fields across space. But this wouldn't allow gravitational information to propagate faster than light. The correlations would only become apparent when classical measurements were compared, respecting the light speed limit. So, quantum entanglement doesn't provide a route to faster-than-light gravity. Another possible loophole comes from theories with extra dimensions. String theory, one approach to unifying gravity with quantum mechanics, suggests that space-time might have more than the three spatial dimensions and one time dimension we directly observe. The extra dimensions might be curled up at tiny scales, invisible to our experiments. In some higher dimensional scenarios, gravitons might propagate through the full higher dimensional space, while light and matter are confined to our four-dimensional brain. If so, gravitons could take shortcuts through the extra dimensions, appearing to travel faster than light from our perspective. Imagine ants walking on the surface of a long cylinder. From their perspective, the shortest path between 2 points is along the cylinder's surface. But if one ant could travel through the third dimension, cutting straight across the cylinder's interior, it could reach the destination faster. To the surface-bound ants, this might look like faster-than-light travel, even though the traveling ant never exceeded light speed in the full three-dimensional space. Could gravitons take similar shortcuts through extra dimensions? The GW170817 observation constrains this possibility. If gravitons traveled significantly faster than light by taking shortcuts, gravitational waves would arrive noticeably before light from the same source. But gravitational waves and gamma rays arrived within 1.7 seconds after 130 million years of travel, ruling out significant shortcut effects. Either the extra dimensions, if they exist, don't allow meaningful shortcuts, or gravitons don't actually travel through them in ways that would speed up their propagation. Current observations suggest gravity travels at light speed even if extra dimensions exist. Some exotic theories propose modifications to Einstein's relativity that might allow faster-than-light travel without causing causality paradoxes. These theories, collectively called deformed special relativity or doubly special relativity, suggest that the structure of space-time might be slightly different at very high energies or very small scales. In some versions, different particles might have slightly different maximum speeds, or the speed limit itself might depend on energy. If gravitational waves at different frequencies traveled at slightly different speeds, we might observe dispersion. The gravitational wave signal would spread out over time as different frequencies arrived at different times. LIGO has looked for such dispersion effects in gravitational wave signals. Within observational precision, no dispersion has been detected. All frequencies of gravitational waves travel at the same speed, and that speed matches light speed to within the tight constraints mentioned earlier. The accumulated evidence strongly suggests that gravity travels at exactly the speed of light, in all circumstances tested so far, with no loopholes or exotic effects allowing faster propagation. But might future observations reveal subtle deviations? Could there be regimes, perhaps near black hole horizons, or during the Big Bang, or at quantum gravity scales where gravity's speed differs slightly from light speed? These remain open questions at the frontier of physics. The regimes where quantum gravity effects become important are far beyond our current experimental reach. We can't recreate the extreme conditions near black hole singularities or during the Big Bang's first moments in terrestrial laboratories. We must rely on astrophysical observations and theoretical reasoning. As you drift in peaceful relaxation, consider how thoroughly the universe has been explored through gravitational waves. In just a few years, from 2015 to the present, we've detected dozens of merging black holes and several merging neutron stars. Each event provides a test of general relativity in strong field regimes, checking whether Einstein's equations continue to work when gravity is intense and dynamical. So far, general relativity passes every test. The gravitational wave signals match theoretical predictions with stunning precision. Gravity propagates at light speed, space-time ripples as Einstein described, and the universe operates according to rules we're beginning to understand. Yet, our understanding remains incomplete. General relativity describes gravity beautifully at large scales, but it's fundamentally incompatible with quantum mechanics, which describes the microscopic world. Somehow, these theories must be unified into a theory of quantum gravity, and in that unification, new insights about gravity's fundamental nature, including its propagation speed, might emerge. The quest to understand gravity at quantum scales is one of physics' greatest challenges. It takes us to the intersection of our two most successful theories, to the edge of what current mathematics and experiments can address, and to the deepest questions about the nature of reality itself. General relativity and quantum mechanics are two pillars of modern physics. Each is extraordinarily successful in its domain. General relativity describes gravity, black holes, cosmology, and the large-scale structure of the universe with remarkable accuracy. Quantum mechanics describes atoms, molecules, chemistry, condensed matter physics, and particle physics with equal success. But these theories are fundamentally incompatible. General relativity treats space-time as a smooth, continuous fabric that curves in response to matter and energy. Quantum mechanics treats everything as quantized, coming in discrete chunks with inherent uncertainty in measurements and wave functions describing probability amplitudes. When we try to combine them, applying quantum principles to gravity, we encounter profound problems. Calculations that work perfectly well for other forces produce infinities when applied to gravity. The mathematical techniques physicists use to make sense of quantum field theories fail for quantum gravity. This suggests we need a new framework, a theory of quantum gravity that seamlessly incorporates both quantum mechanics and general relativity. Several approaches have been developed, each with different implications for how gravitational effects propagate at quantum scales. String theory proposes that the fundamental constituents of nature aren't point particles but tiny one-dimensional strings. Different vibration patterns of these strings correspond to different particles. A particular vibration pattern of a closed string acts like a graviton, the quantum of gravitational field. In string theory, gravitons emerge naturally from the mathematics. They're massless and travel at light speed, just as classical general relativity predicts. However, string theory also predicts corrections to general relativity that become important at very high energies or near singularities like black hole centers. These corrections might slightly modify how gravitational waves propagate in extreme environments. For instance, near a black hole's event horizon, quantum string effects might cause gravitational waves of different frequencies to travel at slightly different speeds, creating a tiny amount of dispersion. The effect would be far too small to detect in current observations, but future, more sensitive gravitational wave detectors might reveal such quantum signatures. String theory also predicts extra dimensions, typically 6 or 7, beyond the familiar 4 spacetime dimensions. These extra dimensions are thought to be curled up at incredibly small scales, far below anything we can currently observe. The geometry of these extra dimensions affects how gravitational waves propagate, though as mentioned earlier, observations severely constrain any effects that would make gravity travel faster than light. Another approach to quantum gravity is loop quantum gravity, which suggests that space-time itself has a discrete, granular structure at the smallest scales. Space isn't perfectly continuous, but is made of tiny chunks, called quanta of space, with sizes around the Planck length, about 10 to the power of negative 35 meters. Time might similarly be quantized into Planck time intervals, about 10 to the power of negative 43 seconds. If space-time is granular, gravitational waves propagating through it might experience effects analogous to light traveling through a medium. Different frequencies might travel at slightly different speeds, depending on how they interact with spacetime's quantum structure. This would create dispersion, with high-energy gravitational waves traveling slightly faster or slower than low-energy ones. Loop quantum gravity calculations suggest these effects would be extraordinarily tiny, undetectable with current instruments. But they make specific predictions that might be testable with future, more sensitive gravitational wave detectors or through observations of gravitational waves from the early universe. A third approach, called causal set theory, models space-time as a discrete set of events with causal relationships between them. In this view, space-time isn't a continuous manifold, but a network of causally connected points. Gravitational waves propagating through this discrete causal structure might experience slight randomness or fluctuations, creating a fuzziness in arrival times. Again, these effects would be far too small to detect currently, but they make definite predictions that future observations might test. All these quantum gravity approaches share a common feature. They predict that at accessible energies and length scales, gravity propagates at light speed, matching Einstein's predictions. Only in extreme regimes near singularities, at the Planck scale, or in the earliest moments of the Big Bang, might quantum gravity effects cause noticeable deviations. Another fascinating question at the quantum gravity frontier is whether information can escape from black holes, and how this relates to gravity's speed. Stephen Hawking famously showed that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate, eventually disappearing entirely. But this creates a paradox. According to quantum mechanics, information is never truly destroyed. It might be scrambled or hidden, but in principle, it's always recoverable. Yet, if a black hole evaporates completely, what happens to the information about everything that fell into it? Does the information disappear, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation? This information paradox connects to questions about how gravitational information propagates. If information can escape from black holes, perhaps through subtle correlations in Hawking radiation, it must somehow cross the event horizon, the point beyond which nothing can escape. But how can information cross a boundary from which nothing, not even light, can escape? Various solutions have been proposed. Some suggest that information is encoded in subtle quantum correlations in the Hawking radiation spread out over the entire evaporation process. Others propose that the event horizon has structure we don't currently understand, perhaps involving quantum entanglement between the black hole interior and exterior. These ideas push at the boundaries of what we know about gravity, quantum mechanics, and information. They suggest that the event horizon might not be as absolute a barrier as classical general relativity implies, and that quantum effects might allow information to leak out in ways that don't violate the cosmic speed limit, but nevertheless rescue information from being lost forever. As you rest in deepest comfort, imagine the quantum foam of spacetime at the smallest scales. At the Planck length, spacetime might not be smooth but roiling with quantum fluctuations, virtual particles popping in and out of existence, tiny black holes forming and evaporating, the very geometry of space and time, uncertain and probabilistic. At these scales, the neat division between space, time, matter, and energy might break down. Quantum gravity effects might create exotic phenomena we can barely imagine. But even here, at reality's most fundamental level, the evidence suggests that gravitational influence respects the cosmic speed limit, propagating at light speed through whatever quantum structure underlies, spacetime itself. The quest to understand quantum gravity continues. String theorists refine their calculations, loop quantum gravity researchers develop new techniques, and experimentalists push the boundaries of observational sensitivity, looking for any hint of quantum gravity effects in gravitational waves, cosmic rays, or other astrophysical phenomena. One day, perhaps in your lifetime, we might glimpse the quantum structure of gravity. We might observe effects that reveal how spacetime behaves at the Planck scale, how black hole evaporation works, how the universe began. And in those observations, we'll learn whether gravity's speed remains exactly the speed of light, even in the most extreme regimes, or whether quantum effects create subtle deviations that point toward a deeper understanding of reality. The speed at which gravity propagates doesn't just affect laboratory experiments or gravitational wave detectors. It shapes the entire universe, from the largest scales down to quantum fluctuations. Let's explore how gravity's light speed propagation influences cosmology, the study of the universe as a whole. The story of our universe begins about 13.8 billion years ago, in an incredibly hot, dense state we call the Big Bang. Space itself has been expanding ever since, carrying galaxies away from each other like dots on the surface of an inflating balloon. This expansion isn't galaxies moving through space, but space itself growing, stretching the fabric of the universe. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinary rapid expansion called cosmic inflation. During inflation, space expanded exponentially, doubling in size roughly every 10 to the power of negative 37 seconds. In a mere 10 to the power of negative 32 seconds, a region of space smaller than a proton inflated to a size larger than our currently observable universe. This inflationary expansion was crucial for understanding the universe's large-scale structure. It solved several problems in cosmology, including the horizon problem. Why does the universe look roughly the same in all directions when widely separated regions couldn't have been in causal contact since the Big Bang? The solution involves gravity's finite propagation speed. Before inflation, the regions that now appear disconnected were actually close together. Within each other's light horizons, the distance light and gravity could travel since the Big Bang. They reached thermal equilibrium, ensuring they had the same temperature and properties. Then inflation rapidly expanded space, pushing these regions far apart beyond each other's horizons. Today, we see these regions in opposite directions in the sky, and they look remarkably similar because they were once in causal contact. But since inflation, they've been beyond each other's horizons, unable to influence each other because gravitational influences and everything else travel at light speed, and the intervening space has expanded. Faster than light can cross it. Wait, didn't we just say nothing can travel faster than light? How can space expand faster than light? The resolution is subtle. The cosmic speed limit prevents objects from moving through space faster than light, but it doesn't limit how fast space itself can expand. During inflation, space expanded so rapidly that distant regions receded from each other faster than light, but this doesn't violate relativity because nothing actually moved through space faster than light. This distinction is crucial for understanding cosmology. The observable universe, everything we can potentially see, is limited by the horizon distance. How far light and gravitational waves could have traveled since the Big Bang. Beyond this horizon lie regions of space that we can never observe because light from them hasn't had time to reach us yet. If gravity propagated instantaneously, this horizon wouldn't exist. Gravitational influences from arbitrarily distant objects would affect us immediately, but because gravity travels at light speed, our universe has a horizon, a boundary beyond which we cannot receive information. This horizon shapes the observable universe's structure and evolution. After inflation, the universe continued expanding, but much more slowly. Matter gradually clumped together under gravity's influence, forming the first stars, galaxies, and galaxy clusters. This structure formation process depends critically on how fast gravitational influences propagate. Computer simulations of cosmic structure formation must account for gravity's finite speed. If gravity were instantaneous, structure would form differently. Matter would clump together more efficiently, responding immediately to gravitational influences from distant regions. The cosmic web, the large-scale pattern of galaxies and voids we observe, would look different. With gravity propagating at light speed, structure formation proceeds more gradually. Small overdensities in the early universe regions slightly denser than average grow as their enhanced gravity attracts nearby matter. This process takes time because gravitational influences propagate at finite speed. The resulting structure matches observations, with galaxies organized into filaments and clusters separated by vast voids. The finite speed of gravity also affects galaxy cluster dynamics. These massive structures, containing hundreds or thousands of galaxies, are held together by gravity, despite galaxies moving at hundreds of kilometers per second. The gravitational potential takes time to adjust to galaxies' motions, creating subtle dynamical effects that wouldn't occur if gravity were instantaneous. One of cosmology's greatest mysteries is dark energy, a form of energy causing the universe's expansion to accelerate. Observations show that distant galaxies are receding faster than they should if gravity were the only force acting. Some invisible influence is pushing space apart, overwhelming gravity's attractive force on cosmic scales. The nature of dark energy remains unknown. It might be a cosmological constant, an intrinsic energy of empty space itself, or it might be a dynamic field, changing over time. Or it might indicate that general relativity needs modification on cosmic scales. Many modified gravity theories have been proposed to explain cosmic acceleration without dark energy. These theories change how gravity works on large scales, potentially affecting how fast gravitational influences propagate or how they depend on distance. The observation of GW 170817, where gravitational waves and light traveled at the same speed, severely constrained many modified gravity theories. Any theory predicting that gravitational waves travel significantly faster or slower than light is now ruled out by observations. The modification, if it exists, must be subtle, affecting gravity's strength but not its propagation speed. This constraint dramatically narrowed the dispersed range of viable modified gravity theories. It suggests that if general relativity needs modification to explain dark energy, the modification likely involves new fields or effects that don't change gravity's basic propagation speed. Another cosmic mystery is dark matter, invisible substance that appears to make up about 85% of the universe's matter. Dark matter doesn't emit, absorb, or reflect light, but its gravitational influence is unmistakable. Galaxies rotate faster than expected based on visible matter alone. Galaxy clusters contain more mass than we can see, and gravitational lensing reveals dark matter's distribution throughout the universe. The distribution of dark matter on cosmic scales depends on how gravitational effects propagate. Computer simulations of cosmic structure formation, including dark matter's gravitational clumping, must account for gravity traveling at light speed. The resulting structures, how dark matter halos surround galaxies, how it's distributed in galaxy clusters, match observations when gravity propagates at light speed. If gravity traveled at a different speed, dark matter's distribution would differ. The fact that observations match simulations using light-speed gravity provides independent confirmation that gravity propagates, as Einstein predicted. The cosmic microwave background, CMB radiation, the afterglow of the Big Bang, provides another test of gravity's speed. This radiation, emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, shows tiny temperature fluctuations, reflecting density variations in the early universe. These fluctuations contain information about primordial gravitational waves generated during inflation. As these waves passed through the early universe's plasma, they created distinctive patterns in the CMB's polarization. Detecting these patterns would confirm inflation and reveal conditions in the first instance after the Big Bang. The predicted CMB polarization patterns depend on gravitational waves propagating at light speed. If gravity traveled faster or slower, the patterns would differ. Future CMB experiments aim to detect these subtle polarization patterns, providing another test of gravity's speed in the extreme conditions of the early universe. The expansion of the universe itself interacts fascinatingly with gravity's propagation. As space expands, it stretches gravitational waves, lowering their frequency, an effect called cosmological redshift, identical to the redshift that makes distant galaxies appear redder than nearby ones. Gravitational waves detected by LIGO have traveled millions or billions of years through expanding space. During their journey, they've been redshifted, their frequencies reduced. By measuring the observed frequency and comparing to theoretical models of the source's original frequency, scientists can determine how much the universe expanded during the wave's journey, providing information about cosmic expansion history. This works only if gravitational waves travel at light speed. If they traveled faster or slower, the relationship between source frequency, observed frequency, and cosmic expansion would differ. The fact that observations match predictions assuming light speed propagation provides yet another confirmation of gravity's speed. As you drift towards sleep, imagine the vast cosmos shaped by gravity's light speed propagation. The horizon limiting what we can observe, the structure of galaxies and galaxy clusters, the expansion rate, the distribution of dark matter. All these cosmic features depend on gravity, traveling at precisely the speed of light. The universe is a tapestry woven by gravitational influences propagating at light speed across billions of years and billions of light years. Each thread connects distant regions causally, binding the cosmos together while maintaining the orderly progression of cause and effect that makes reality comprehensible. In this cosmic tapestry, we're a single thread, a brief moment of consciousness in a tiny corner of space and time. But through science, we've learned to read the tapestry, to understand the patterns woven into it, to glimpse the fundamental principles governing reality. And one of those principles, confirmed now beyond doubt, is that gravity travels at exactly the speed of light. Despite the strong evidence that gravity travels at light speed, many questions remain. The frontiers of gravitational physics are alive with ongoing research, new experiments, and theoretical developments that might reveal subtle aspects of gravity we don't yet understand. Let's explore some of these open questions and the experiments designed to address them. One of the most pressing questions is whether gravitons, the hypothetical quantum particles carrying the gravitational force, actually exist. In quantum field theory, forces are mediated by particles, photons for electromagnetism, W and Z bosons for the weak nuclear force, gluons for the strong nuclear force. By analogy, gravity should be mediated by gravitons, but detecting individual gravitons is extraordinarily difficult. Gravitons interact far more weakly with matter than any other particle. A single graviton passing through solid lead would have only about 1 chance in 10 to the power of 80 of interacting with a lead atom, essentially zero. Building a detector sensitive enough to catch individual gravitons seems hopeless with any foreseeable technology. Nevertheless, physicists are exploring indirect ways to detect gravitons' quantum properties. One approach involves looking for quantum effects in gravitational waves. If gravitons exist and have quantum properties, gravitational waves should exhibit quantum noise, random fluctuations, due to the discrete, quantized nature of gravitons. LIGO and future gravitational wave detectors might eventually detect this quantum noise. It would appear as a slight randomness in gravitational wave, signals beyond what classical noise sources predict. Detecting this quantum noise would confirm that gravity, like other forces, is quantized at the fundamental level. Another approach involves tabletop experiments testing whether gravity can create quantum entanglement between objects. If two masses in quantum superposition interact only gravitationally, and if gravity is mediated by quantum particles, gravitons, the masses should become entangled. Detecting this entanglement would prove that gravity has quantum properties. Proposed experiments use tiny objects, perhaps microscopic diamonds or nanospheres, cooled to near absolute zero and placed in quantum superpositions of different positions. If gravitons mediate the gravitational attraction between them, the objects should become entangled through graviton exchange. Detecting this entanglement is extraordinarily challenging, but might be possible within the next decade or two. Another open question concerns whether gravity's speed might vary slightly depending on the gravitational wave's frequency or energy. While current observations constrain any such variation to less than 1 part in 10 to the power of 15, some quantum gravity theories predict tiny frequency-dependent effects that might be detectable with more sensitive instruments. Loop quantum gravity, for instance, predicts that spacetime's granular structure might cause high-frequency gravitational waves to travel slightly faster or slower than low-frequency waves. The effect would be minute, but it would accumulate over the billions of light-years these waves travel. Future gravitational wave detectors, with greater sensitivity across wider frequency ranges, will test these predictions. If different frequencies arrive at detectably different times from the same source, it would provide evidence for quantum gravity effects and reveal something about spacetime's structure at the smallest scales. The third-generation gravitational wave detectors, already being planned, including Cosmic Explorer in the United States and Einstein Telescope in Europe, will be about 10 times more sensitive than LIGO. They'll detect mergers throughout most of the observable universe, providing thousands of events to analyze for subtle effects like frequency-dependent propagation speeds. Another frontier involves testing gravity in extreme environments we can't currently access. The regions near black hole event horizons, where gravity is strongest, might reveal effects not predicted by classical general relativity. Frame dragging the way a spinning black hole twists spacetime around it might affect how gravitational waves propagate. The Event Horizon Telescope, which captured the first image of a black hole shadow, continues to improve its capabilities. Future observations might detect subtle effects in how light and gravitational effects propagate near black holes, testing whether Einstein's predictions hold even in these extreme environments. Another extreme environment is the early universe, particularly during the first moments after the Big Bang. Conditions then were so extreme that quantum gravity effects might have been significant. Primordial gravitational waves from inflation, if detected, would carry information about physics in that epoch. Several experiments are searching for these primordial waves by looking for their imprint on the cosmic microwave background radiation. The BICEP and Planck satellites have placed constraints on primordial gravitational waves, and future experiments like CMB-S4 and LIGHTBIRD will be more sensitive. Detecting primordial gravitational waves would not only confirm inflation, but would also test gravity's behavior in the extreme conditions of the early universe. The wave spectrum would reveal whether gravitational waves propagated at light speed even when the universe was hot, dense, and filled with exotic quantum fields. Another open question involves whether all forms of energy gravitate equally. Einstein's equivalence principle states that gravitational mass and inertial mass are identical objects, fall at the same rate, regardless of their composition. The microscope satellite, which operated from 2016 to 2018, tested this principle to unprecedented precision, finding no violations to about 1 part in 10 to the power of 15. But could there be subtle violations at even higher precision? Some theories suggest that dark matter or dark energy might interact with gravity slightly differently than ordinary matter. Testing the equivalence principle with ever greater precision might reveal these differences. Future satellites and experiments will push equivalence principle tests to even higher precision. Any violation, however small, would revolutionize physics, potentially revealing new forces or interactions we haven't discovered yet. Another question involves whether gravitational waves from different sources might reveal unexpected phenomena. Most detected gravitational waves come from binary black hole or neutron star mergers, but other sources might exist. Supernova explosions, rapidly spinning neutron stars, or even cosmic strings, hypothetical topological defects from the early universe, might produce detectable gravitational waves. Each source type would test gravity in different regimes. Supernovae involve complex hydrodynamics and nuclear physics. Rapidly spinning neutron stars test how gravity interacts with extreme matter densities. Cosmic strings, if they exist, would reveal aspects of the early universe's phase transitions. As gravitational wave detectors become more sensitive and additional detectors come online, including CAGRA in Japan and LIGO India, the catalogue of detected events will grow rapidly. This population will reveal whether any unexpected sources exist and whether all gravitational waves propagate at light speed regardless of their origin. Another frontier involves testing gravity on the smallest scales accessible to experiment. While general relativity describes gravity beautifully at large scales, we don't know whether it continues to work at microscopic distances. Some theories suggest that gravity might be modified at scales below a millimeter due to extra dimensions or other exotic effects. Experiments testing gravity at small scales use sophisticated apparatus to measure gravitational forces between objects millimeters or micrometers apart. These experiments are extraordinarily challenging at such small scales. Electromagnetic forces dominate, and isolating the tiny gravitational signal requires careful control of all other forces. Recent experiments have tested gravity down to scales of about 50 micrometers, finding no deviations from Newton's inverse square law, suitably modified by general relativistic corrections. Future experiments aim to probe even smaller scales, potentially revealing modifications that would point toward new physics. As you rest peacefully, imagine scientists around the world pushing the boundaries of gravitational physics. Some build ever more sensitive detectors, capable of measuring distortions smaller than an atomic nucleus. Others develop theoretical frameworks, seeking mathematical structures that might underlie quantum gravity. Still others analyze data from gravitational waves, cosmic microwave background radiation, and other sources, looking for subtle signatures of effects beyond Einstein's theory. This ongoing quest drives fundamental physics forward. Each answer raises new questions. Each observation constrains theories and inspires new ideas. The question of gravity's speed, now answered definitively for the regimes we can currently test, opens into deeper questions about quantum gravity, the universe's earliest moments, and the fundamental structure of reality. Beyond the equations and experiments, the discovery that gravity travels at light speed carries profound philosophical implications. It shapes how we understand causality, connection, time, and our place in the cosmos. Let's explore these deeper meanings. The finite speed of gravity establishes a fundamental limit on causal influence. Nothing, not matter, not energy, not even gravitational effects can propagate faster than light. This cosmic speed limit isn't just a practical constraint, but a deep feature of reality's structure. Why should such a limit exist? In special relativity, the speed limit emerges from the principle that the laws of physics are the same for all observers moving at constant velocity. If information could travel faster than light, different observers would disagree about the order of cause and effect. Events that appear causally connected to one observer might appear disconnected or reversed to another observer moving relative to the first. The light speed limit prevents these causality violations. It ensures that all observers, regardless of their motion, agree on the causal structure of events. Cause always precedes effect. Information propagates forward in time, never backward. The universe maintains a coherent narrative of cause and effect. Gravity's propagation at light speed fits perfectly into this framework. If gravitational effects traveled faster than light, they could create causality paradoxes. A massive object's gravitational influence could affect its own past, creating logical contradictions. By propagating at light speed, gravity respects causality and maintains reality's logical coherence. This has philosophical implications. It means the universe operates according to rules, not chaos. The past influences the future through chains of causation that propagate at finite speed. This orderly progression from past to future makes the universe comprehensible, allowing science to make predictions and understand phenomena. The finite speed of gravity also creates a peculiar relationship between events and knowledge. When you look at a star 1,000 light-years away, you see it as it was 1,000 years ago. Similarly, its gravitational influence on you is also delayed by 1,000 years. The star's now and your now are fundamentally disconnected. There's no universal present moment that includes both you and the star. Einstein called this the relativity of simultaneity. Events that appear simultaneous to one observer occur at different times for observers moving relative to the first. This means now is observer-dependent, not an absolute universal feature of reality. This challenges our everyday intuition. We imagine that now is a single moment encompassing the entire universe, with everything that exists having a definite state at this instant. But relativity reveals this as an illusion. Now is a local concept defined by light and gravitational horizons, the distances light and gravity can travel. For practical purposes on Earth, where distances are tiny and gravitational signals take microseconds to propagate, we can approximate a universal now. But, cosmologically, this approximation breaks down. The observable universe has no single now, only a patchwork of locally defined presents, stitched together by light-speed signals propagating across space. This creates a curious separation between being and knowing. A star might have exploded centuries ago, but until its light and gravitational waves reach us, we remain ignorant of this fact. In some sense, from our perspective, the star still exists, yet, in the star's reference frame, it's long gone. Which perspective is real? Relativity suggests both are equally valid. Reality isn't a single universal state, but a complex space-time structure, with different observers accessing different slices through this structure. The speed of gravity, by determining how fast causal information propagates, shapes how these slices relate to each other. The finite speed of gravity also affects how we think about connection and isolation. On one hand, every massive object in the universe is gravitationally connected to every other object. The gravitational influence extends infinitely, diminishing with distance but never quite vanishing. In this sense, everything is connected, part of a cosmic whole bound together by gravity. On the other hand, the finite propagation speed creates isolation. Regions beyond our horizon are permanently disconnected, unable to influence us because light and gravitational signals from them will never reach us in the age of the universe. Even within our horizon, The time delay means we're always receiving information from the past, never the present. This tension between connection and isolation mirrors human experience. We reach out to others, form relationships, share experiences, yet perfect communication is impossible. We're each trapped in our own minds, experiencing reality from our own unique perspective, connected to others through signals that take time to propagate. The gravitational web binding the cosmos becomes a metaphor for the social web binding humanity. Both involve connections that take time to propagate, that carry information about the past, that create networks of influence spanning vast distances. Both involve fundamental limits: speed of light for physical signals, various biological and technological limits for human communication that shape how the network functions. Another philosophical implication involves the nature of time itself. In Newton's universe, time was absolute, flowing uniformly everywhere. Gravity acted instantaneously across space, independent of time. But in Einstein's universe, time and space are intertwined into spacetime, and gravity is spacetime curvature. The propagation of gravitational waves at light speed reveals that time and space are on equal footing. Just as you can't be in two places at once, you can't receive information about an event before light or gravitational waves from that event reach you. Time isn't a parameter separate from space, but one dimension of a four-dimensional space-time fabric. This reconceptualization affects how we think about time's passage. Why does time seem to flow forward, from past to future? Why do we remember the past but not the future? These questions connect to thermodynamics and entropy, but also to causality and the cosmic speed limit. If information could travel backward in time, or equivalently faster than light, the distinction between past and future would break down. We could know the future as easily as the past. The flow of time would lose its directionality. But with the cosmic speed limit, including gravity's light speed propagation, time maintains its arrow, flowing forward in the direction of increasing causality. The discovery that gravity travels at light speed also reveals the deep unity underlying nature's forces. Gravity and electromagnetism, despite seeming very different, propagate at the same speed. This hints at a fundamental connection between them, perhaps pointing toward a unified theory incorporating all forces. Historically, physics has progressed by finding such unifications. Maxwell unified electricity and magnetism. The electroweak theory unified electromagnetism and the weak nuclear force. Perhaps eventually we'll unify all forces, including gravity, into a single theoretical framework. The fact that gravity and light share a propagation speed suggests this unification is possible, that beneath apparent diversity lies unity. This philosophical principle, that the universe is ultimately unified and comprehensible, has driven science since its inception. The success of this approach, from Newton to Einstein to the standard model of particle physics, suggests the principle is true. The universe operates according to rules we can discover, connections we can trace, patterns we can understand. As you drift into sleep, consider what the speed of gravity reveals about reality. The universe is causal but not deterministic, allowing both order and possibility. It's unified but diverse, with different forces sharing common features yet behaving distinctly. It's comprehensible yet mysterious, with each answer revealing new questions. The speed of gravity, precisely measured and theoretically understood, is a thread connecting these philosophical insights. It shapes causality, defines horizons, limits knowledge, and reveals unity. In understanding this single number, 299,792,458 meters per second, we glimpse something profound about existence itself. As our journey through the speed of gravity draws to a close, let's reflect on what we've discovered. The question we began with, does gravity travel faster than light, has been answered definitively. Gravity propagates at exactly the speed of light, no faster and no slower. This simple answer encompasses a century of scientific progress, From Einstein's theoretical predictions to LIGO's extraordinary detections, from binary pulsar observations to neutron star merger measurements. The accumulated evidence leaves no doubt. Gravitational waves travel at light speed to within 1 part in 10 to the power of 15, effectively exactly equal. But the journey to this answer revealed much more than a single number. It showed us that gravity isn't a force, but space-time curvature, that space-time isn't a rigid stage, but a dynamic fabric that can ripple and wave, that the universe speaks to us not just through light, but through gravitational waves, allowing us to hear cosmic events invisible to conventional telescopes. The discovery opened gravitational wave astronomy, a new way of observing the universe. Since 2015, LIGO and its partner detectors have observed dozens of gravitational wave events, merging black holes, colliding neutron stars, and perhaps exotic phenomena yet to be identified. Each detection refines our understanding of how these systems form and evolve, tests general relativity in strong field regimes, and reveals the universe in ways impossible before. The measurement of gravity's speed through the GW170817 neutron star merger in 2017 stands as one of the great scientific achievements. For the first time, humanity measured how fast gravitational influence propagates, confirming Einstein's century-old prediction with extraordinary precision. This measurement ruled out numerous alternative gravity theories, constraining how gravity can behave and pointing toward the correct theoretical framework. Yet despite these triumphs, many questions remain. How does gravity behave at quantum scales? Can we detect individual gravitons? Does space-time have granular structure at Planck scales? How did supermassive black holes form so quickly in the early universe? What is dark energy and dark matter? How do we unify gravity with quantum mechanics? These open questions ensure that gravitational physics remains an active, vibrant field. Future detectors, third-generation ground-based observatories, space-based interferometers like LISA, tabletop quantum, experiments will probe gravitational phenomena with ever greater sensitivity. Theoretical physicists continue developing frameworks that might unify gravity with other forces, searching for mathematical structures underlying quantum gravity. The journey of discovery continues. Each answer raises new questions. Each observation constrains theories and inspires new ideas. The question of gravity's speed, now resolved for the regimes we can test, opens into deeper questions about nature's fundamental principles. As you rest in complete comfort, feel Earth's gentle gravitational embrace holding you safely in place. This force, reaching from the planet's center to where you lie, travels at exactly the speed of light. Every moment, gravitational influence propagates outward from Earth at 299,792 kilometers per second, binding the Moon in its orbit, affecting the Sun and planets, connecting Earth to the gravitational web spanning the cosmos. Imagine the Sun 150 million kilometers away. Its gravitational influence reaches Earth about 8 minutes and 20 seconds after being generated. If the Sun somehow vanished right now, we'd continue orbiting the empty space for 8 minutes, unaware of its absence, until the gravitational change and final photons arrived simultaneously. This 8-minute delay, this cosmic time lag between cause and effect, is fundamental to reality's structure. It ensures causality, prevents paradoxes, and maintains the orderly progression from past to future that makes the universe comprehensible. Picture gravitational waves from distant cosmic cataclysms passing through your body right now. Merging black holes billions of light years away, neutron stars colliding in distant galaxies. Perhaps exotic sources, we haven't yet discovered all, send gravitational waves rippling through space-time at light speed. These waves stretch and compress space by amounts far smaller than an atomic nucleus, too small to feel but detectable by humanity's most sensitive instruments. These gravitational waves connect you to the most energetic events in the universe. They're messengers, carrying information about cosmic phenomena invisible to light-based astronomy. Through them, we've learned that black holes are common, that neutron star mergers create heavy elements like gold and platinum, that space-time really does ripple and wave, as Einstein predicted. Consider the precision required to detect these waves. LIGO measures changes in distance of 1 part in 10 to the power of 21, like measuring the distance to the nearest star to an accuracy smaller than a human hair. This precision represents perhaps humanity's greatest technological achievement, showing what's possible when we push physics and engineering to their absolute limits. Think about the journey from ancient Greece to modern gravitational wave astronomy. From Aristotle's natural places to Newton's universal gravitation, to Einstein's curved spacetime, to LIGO's detections, each step built on previous understanding. Each generation pushing knowledge forward, asking deeper questions, demanding better answers. This progression testifies to science's cumulative nature. We don't just accumulate facts, but build ever better frameworks for understanding reality. Newton's theory wasn't wrong so much as incomplete, accurate in its domain but failing in extreme regimes. Einstein's theory encompassed and transcended Newton's, remaining accurate today in all tested regimes. Yet Einstein's theory will likely be similarly transcended. A theory of quantum gravity, when finally developed, will probably encompass general relativity while revealing new phenomena at quantum scales or in extreme conditions. This is how science progresses, not through revolution that discards the past, but through evolution that incorporates previous understanding into richer frameworks. The speed of gravity exemplifies this progression. For Newton, it was infinite gravitational effects propagated instantaneously. Einstein predicted light speed propagation but couldn't test it directly. Hulse and Taylor provided indirect evidence through binary pulsars. LIGO detected gravitational waves directly. GW170817 measured their speed. Each step refined understanding, testing predictions with greater precision, confirming or falsifying theories. What makes this progression possible is nature's consistency. The universe operates according to reliable laws. Experiments give reproducible results. Mathematics describes physical phenomena with uncanny accuracy. This consistency isn't logically necessary. We could imagine a chaotic universe with no discoverable laws, but it's apparently true of our universe. Why should nature be comprehensible to human minds? Why should mathematics, an abstract creation of human thought, describe physical reality so perfectly? These questions touch on the deepest mysteries of existence, the relationship between mind and matter, between abstract truth and physical reality. Perhaps, as some suggest, consciousness is fundamental to reality, and the universe is inherently mental. Or perhaps human minds evolved specifically to understand the universe, having been shaped by natural selection operating in this universe with these laws. Or perhaps the correspondence between mathematics and physics points to a Platonic realm of abstract forms underlying reality. These philosophical speculations go beyond physics, but they're inspired by physics' success. The fact that gravity propagates at light speed, that this can be measured and confirmed, that Einstein predicted it from pure mathematical reasoning, all this suggests the universe is deeply rational, operating according to principles our minds can grasp. As consciousness fades into sleep, let these final thoughts accompany you into dreams. You're part of a cosmos, bound together by gravitational influence, propagating at light speed, from the smallest quantum fluctuations to the largest cosmic structures. From the Big Bang to the far future, gravity shapes reality at every scale. The gravitational waves passing through you now, though imperceptible, connect you to distant cosmic events. You're receiving messages from the universe, information encoded in space-time's subtle ripples, carrying news of black holes that merged when the universe was younger, of neutron stars that collided in galaxies far away. These waves travel at precisely the speed of light because reality has a fundamental speed limit, a cosmic constraint, ensuring causality and preventing paradoxes. This speed limit shapes everything: how galaxies form, how the universe expands, how information propagates, how time relates to space. The universe revealed by gravitational wave astronomy is dynamic, violent, filled with extreme phenomena that dwarf human scales. Yet it's also ordered, following mathematical laws, exhibiting patterns we can discover and understand. This combination cosmic grandeur, operating according to comprehensible principles, makes reality both awesome and knowable. Rest now, cradled by Earth's gravity, connected through invisible threads to the cosmic web. As you sleep, gravitational influence continues propagating at light speed throughout the universe. Stars orbit galactic centers, planets circle stars, moons orbit planets, all guided by gravity's gentle but inexorable pull, all connected through spacetime's flexible fabric. The speed of gravity, 299,792,458 meters per second, exactly equal to light speed, is more than a measurement. It's a window into reality's fundamental structure, a clue about how space, time, matter, and energy relate. It tells us that the universe operates according to principles we can discover, that effects follow causes in orderly fashion, that reality is comprehensible. Tomorrow, scientists will continue probing gravitational phenomena, building more sensitive detectors, developing better theories, asking deeper questions. The quest to understand gravity completely, including its quantum nature and ultimate unification with other forces, continues. Each answer reveals new mysteries, new frontiers to explore. But tonight, all this can wait. The universe will still be here tomorrow, still strange, still wonderful, still full of mysteries. For now, sleep peacefully, knowing you've journeyed through one of physics' great questions and found its answer. Gravity travels at the speed of light. Einstein was right. The universe is knowable. And you, briefly, have touched one of its deepest truths. As the final moments of consciousness slip away, imagine once more the gravitational waves rippling through space-time, the invisible currents connecting all matter across cosmic distances. Feel Earth's steady pull, a force that's held you safely throughout your life, that will remain long after you're gone, that connects you to the planet and through the planet to the sun, the galaxy, and ultimately the entire cosmos. Sleep now, wrapped in the gentle embrace of gravity, traveling at light speed from every massive object in the universe to your resting body. The cosmic conversation continues, gravity speaking across the void at precisely 299,792 kilometers per second, neither faster nor slower, exactly as it should be, exactly as Einstein predicted, exactly as observations confirm. The monster at the heart of reality isn't chaos or randomness, but deep order, mathematical beauty, comprehensible principles operating consistently across all scales. We've glimpsed this order through gravity's speed, and in that glimpse, we've understood something profound about the universe we inhabit. Rest deeply. Dream of space-time ripples and cosmic dances, of black holes and neutron stars, of gravitational waves traveling across billions of years to reach us. Dream of humanity's quest to understand, our drive to question, our capacity to discover truths about reality that seem at first impossible to know, and know, as you drift into sleep's quiet darkness, that the universe continues its timeless dance, gravity propagating at light speed through the cosmic expanse, connecting everything that exists through invisible threads woven into space-time's fabric. This is our universe, strange, beautiful, comprehensible, and now, for tonight at least, understood just a little better than before. Good night. The gravitational waves continue their journey across the cosmos, and you, for this brief moment in cosmic time, have understood something fundamental about how they travel. Sleep well, knowing the universe is both grander than imagination and more elegant than dreams. The speed of gravity has been measured, the question answered, and reality revealed to be even more beautiful than we dared hope.